Yeah, hello and welcome. My name is Grauer from University of Rostock, and today I will be presenting about our paper Causality-Informed time series notation models for building prediction performance. So, building prediction performance, we're talking here about HVAC energy prediction, and indoor temperature prediction has highly shifted more towards data-driven approaches. So, and for different reasons, of course, more sensor coverage and so on. And well, the pipeline of analyzing, cleaning data, preparing data, choosing an appropriate model, fine-tuning it, evaluating, maybe refining it until results are satisfying, still means probably way less effort than building up a physical model, running a simulation. This approach can still pretty much be limited by different factors. So data, so parts of it maybe could be missing. We need a lot of data in the first place. We need it to be in high quality. We need to fit our models, and still after that, these models stay highly case-specific on the specific individual building we fit them for, and it's not easy to transfer them to different buildings. So also these standard-driven approaches often tend to learn on correlation instead of physical relations or causation, and so for some of these limitations, recently time series notation models have emerged as a possible solution. So these models are inspired by by LLMs and also utilize a transformer. So they have been trained on, instead of of natural language like large language models, on a large stack of time series data from various domains. So with this brain training, they of course already know common patterns in time series like seasonality, trends, cyclic behavior. In this paper, we focus on their short-term forecasting abilities. And for forecasting, they usually predict the next time steps of a defined prediction horizon of the next time steps based on previous time steps, context window. Also, recent model versions support new extended context, so you can add covariates, you can add correlated time series, you can also forecast multiple time series at a time. And also in the newest version of Amazon Grauer's model, there's in-context learning mechanism where cross-attention promises to benefit the predictive performance by learning in inference time. So with all this being said, this is nice and good, but we have already seen in research that these older versions of these models fail to outperform statistical baselines. So for this paper, we had the research question of can these models help us overcome problems with data quality? How do they perform on different tasks? And is it specific to the task how they perform? And is it possible that we can somehow enforce causality on them and move a little bit away from predicting purely from the time series context? And how can we make use of in-context learning mechanisms? So we choose to compare different models. First of all, we get auto-integrated, auto-regressive integrated moving average, which is our statistical baseline, short ARIMA. We've got two univariate time series forecasting models. One is TSFM, which is explicitly trained only on univariate time series, so only predicting from the context, and also Grauer's 2. And for Grauer's 2, we also have like past only covariates, and in the newer version, we can also paste in future covariates if we already know them. So extend our predictive performance, maybe if we add something from the prediction window. We compare this to graph convolution networks, two kinds of. So one with just two layers of convolution, graph convolution, and one where one layer is a gated recurrent trying to capture temporal patterns. And also we build these graphs and then put this into covariates of Grauer. So another explanation. So for forecasting with covariates only, we limit ourselves to a few highly correlated covariates. For example, if we have a room temperature, this is highly correlated to the outer temperature usually and to the adjacent room temperature. And of course, for realistic reasons, we limit ourselves to known future covariates. So, for example, we can predict work schedules, we can pretty accurately predict the weather for the next hour, but other things we cannot do with that certainty. The graph neural network approach serves as a physics-informed comparison, so we have an underlying directed graph. We build on domain knowledge of physical relations, and we define this as a regression task of predicting the next values with known features containing previous values. And the causal approach, combining both, we feed the graph nodes as covariates, resulting in a high number of covariates. So our prediction horizons were chosen for all models for 1, 2, 4, and 8 hours as basic short-term horizons. And we test this approach on 2 real-world datasets, which is one student dorm, indoor environment, and energy consumption datasets. This is characterized by by a sparse coverage of sensors. So we have a less complex graph representation. For example, we want to predict humidity and HVAC energy usage. If you look at the graph, we have only 6 nodes and 9 edges. So since there's just not more sensors that are governing this. Also, we can see for the energy usage, we have this on-off pattern, which is hard to predict since it depends on unobserved occupant behavior that looks rather arbitrary, and we have not sensed it. So, also we compare this to an office building where we have a dense sensor network of thermal zones, large number of HVAC operational data, fan speeds of individual zones, heating valve positions, and outdoor sensors. This results, for example, for our task, we have zone temperature and HVAC energy consumption in a large graph representation of 150 nodes and 154 edges. So what are the results that we encountered from this? So first of all, for the student dorm, I already mentioned, this is highly governed by behavior that is not measured. So it's also not in the historical context. The model no model was able to capture this dynamic. So it's not somewhere also in the time series data. It's not predictable. Also, all models fail to capture this dynamic. And for the student dorm indoor humidity, we learned that by its definition, humidity can only range from 0 to 100%. Probably ranges more like between 20 and 80. So this seems to benefit our time series foundation models since they outscore all other models. And for a graph convolutional network that is playing from scratch, this is a dynamic that is hard to capture. So we would probably need more sensors or more data to capture this. Comparing this to the office building, we have for the HVAC energy prediction, the GCN model comes close to our predictions of time series foundation models. Surprisingly, TSFM, which is only univariate forecasting, scores the best results up to 4 hours, and then highly decreases when you extend the prediction horizon. And the causal covariates we added here, the high number, seems to decrease performance. So if we compare this also to the thermal zone prediction, we have a reduced complexity prediction here, so temperature is highly autocorrelated, and we have a higher number of relevant features because adjacent temperatures are always pretty much correlated by heat transfer. And so the advantage of time series foundation models is shrinking, and our causal approach, but actually is adding here with the high correlated features. So what can we conclude from this? So we learned that time series foundation models are a strong alternative, especially where high quality data is sparse. But the gap seems to shrink with more data becoming available. The accuracy highly depends on prediction target. So what are the key takeaways, or what do we learn? Can we just happily use time series foundation models now and stop training models from scratch? So of course there are some limitations. We have a lack of explainability. We can append normal models with explainability techniques, but these models have just learned something in pre-training, and we don't know where it's coming from. Also, we limit ourselves to this point to a narrow subset of available data, just the historical context, and we have seen that constraints do not necessarily add to performance. So what we're now looking for is to combine the strengths of zero-shot models with classic machine learning models and maybe explainable causal information. So thank you for your attention, and look forward to your questions.